Good afternoon, everyone. Hope you are still you still have enough energy in the batteries for the last lecture of the summer school. And Ilya, we are very happy that you managed to be back online on time. And if you are ready, you're welcome to start sharing the screen and start with your last lecture. And maybe just for the end time, the reminder that after this lecture, we still have the closing function. So please, if you plan to attend, and I'm sure that all of you want to attend, you need to register to get the link to join. Yeah. So that will be at 3:30 as soon as Ilya's lecture is finished. Yeah. Okay. And I see there is a request to finish assignments by midnight tonight. I think we can be generous and give you the whole weekend if you want to finish assignment. And I hope Daniel from the CHPC will not be upset with me if I do this generous gesture. Yeah. But I think it would be just all right. Yeah. Okay, Ilya, sorry. This was the service announcement. You are welcome to start.
Let's see if it works. Okay, yeah. I think it's kind of working, yeah. You should be able to see my iPad screen.
Yeah, perfectly.
Okay. So today is our last lecture in this mini series on kind of open quantum systems and kind of question of simulation of open quantum systems. And today we are going to kind of, in some sense, to wrap up the story with a very unusual view on the dynamics of the open quantum systems, but very natural and probably the first, historically, that was one of the first views which was developed, but afterwards it's gone away and it's came back only in 90s, kind of in the full force. Okay. What we're going to talk about, first I'm going to remind you about the Brownian motion and how that process could be done. Kind of, it was kind of, as you know, the Brownian motion was first kind of discovered experimentally and afterwards explained by Einstein and Smoluchowski independently, and it was done using some statistical ideas, something like a density matrix approach. And afterwards, Langevin suggests that you can do it from his point of view much better using an object which he didn't call that way, but it will be called later. It's called stochastic differential equation. Okay, so afterwards, and I'm going to kind of give you the brief introduction and give you kind of the result which relate this kind of density matrix equation, but density matrix equation in some sense classical density matrix equations, which are called Fokker-Planck equations and corresponding stochastic equations. We are going to use as an example for unraveling a very simple example of dumb harmonic oscillator, and I was planning to tell you more about the kind of how to describe photons and how to describe systems with photons and bosons, and kind of because I essentially wasted my first lecture by writing and not preparing lectures. Sorry for that. That's why I'm just going to very extremely briefly mention that, because we'll need to use it for naive idea of unraveling, or how you can make a correspondence between the density matrix and wave function. And afterwards, we're going to talk about a little bit about stochastic Schrödinger equation, and I will finish up just with the result, which is called unraveling with help of piecewise deterministic processes, which is now kind of nice theoretical results, which is, as you will see, was slightly different from that what we can do out of the naive unravelings. Okay, so let's start. Oops. I pour some water on the iPad. Hopefully it will survive. Sorry. Okay. Okay. So Brownian motion. Yes, it was kind of discovered by the Robert Brown, and that's why it's after been called Brownian motion. And essentially, he was a botanist who was making some observation, and he's seen that small pollen grains in the water and any other liquid kind of moves chaotically, and he was very curious, kind of, are they become to be, is it property of life, or is it property of kind of life matter, or not life matter? But afterwards it was found out that everything, whatever, if it's small enough, you put it into the liquid, suspended in the liquid, it will begin to move chaotically. And yeah, that was quite curious why. And as I mentioned, the first explanation of that was suggested by Einstein and Smoluchowski independently in 1905 and 1906. As you see, that 1905 was extremely productive year for Einstein. And the approach which they took was kind of statistical approach or probabilistic approach, or it's called the kind of probabilistic theory of the Brownian motion. And just an example of the Brownian motions to you, I just went to Wikipedia, type in Brownian motion, and there is a picture, so we can see that there is some kind of random trajectories, and we're going to see in the tutorial how we can generate similar trajectories. Okay, so, and I'm going to very briefly kind of go through the Einstein's argument. It's very simplistic and kind of very straightforward, but it's have a
Ilya, are you there? I think you are frozen. Ilya, it seems you are frozen. Just a second, I tried to, what happened? I think Ilya might be trying to reconnect. Let's wait a second and see what happens. I think Ilya is back. Ilya, are you back? I can see you, but we can't hear you. Okay. Hello, Ilya?
sorry, that was my super reliable mobile data. Sorry for that. Let me just reshare my screen.
Welcome back.
No, it just went blank. Sorry. I hope that will be the only one. Okay, so screen, back to screen. Okay. Okay, so we were somewhere here. Okay, let's keep going. Okay, so each particles are moving independently. So, and there is some kind of, and again, very, very similar to, sorry, there is something in the chat. Yes, okay, so that's Francesco reminded about the book voucher. So let me open the chat so that I could keep an eye on it. Okay, so, and again, very similarly, as we were talking about open quantum systems, but this is a pre-open quantum systems stuff, you still need always to talk about the timescales. And so you'll consider that everything, kind of each motion is happening on some timescale tau, such that each individual motion is independent from each other. So, and the change of the coordinate is kind of coordinate x is changed by some delta, which delta could be positive or negative, so it could be added left or right. Yes, it can push you in one direction or on another direction because of existence some, as Einstein said, the frequency law for delta. I mean, on the modern language, it's that there is some probability distribution for delta, such that it gives you the probability that you're going to go some distance delta in one direction or in another direction. And of course, as a probability distribution, this quantity needs to be normalized. And it's just because there is no reason to distinguish between left and right, it will be symmetric with respect to left and right. Okay. And kind of this, and if we have kind of probability distribution of kind of function which corresponds to distribution of deltas, and this function is denoted by phi of delta. So we can say that the number of particles which are drifting between the distances delta and delta plus delta will be described by something like this. Yes, so kind of it's our total number of particles on kind of probability to get shift delta on small delta. Okay, so this function is normalized on 1, and this function will be typically something which is considered to be quickly decreasing function. So it means that it's very likely to move a little bit, and it's very unlikely in one go to make a big jump. And it's because there is no reason to distinguish left and right, it's symmetric. Okay, so, and if now we introduce a function, which is called the number of particles per unit volume. So we just kind of counting, so we just consider small volumes and we count number of particles, and that will be this function. So we could see what happening in the point x, so in the volume x, yeah, after small time tau, and it will be related to the all possible kind of jumps into that area from the neighbors. And for small taus, we can do the expansion in time. So because this function is also falling away very quickly, and this is small as well, we can also do expansion in delta, and we'll get something like that. And if in time, because we know the answer, we can already say that in time it will be enough first order in tau. In delta, we need the second order in tau or in delta, because this term will go to 0. So now we just substitute it back into this equation. So this is our f plus delta t. And that is our expression. Okay, so this, we get the first term, this is equal to 1 by normalization. This function is symmetric. This is antisymmetric, so we get the antisymmetric function in the symmetric interval. So this integral 0. That's why the first order term doesn't give us contribution. And we have only second order term. F here and F here cancel out. And we now, because tau is some characteristic time scale, we can just put all of this together into some constant d, which is traditionally called diffusion constant. And what we get a partial differential equation, very famous partial differential equation, which is called diffusion equation, which exactly describes to us evolution of Brownian particles and all other possible diffusion process. For example, how the smell propagate in the air, and so on and so forth. Okay, so we have a diffusion equation, and it has a standard solution, which is given by the exponential in x and linear in t. Yeah, and what we can kind of calculate from here, we can calculate what is the average x squared. So we just need to multiply this by x squared and integrate from minus to plus infinity. We're going to get expression like this, which if we're going to measure what is the average square this, because average will be equal to 0. Yes, because average x, sorry, average x will be equal to 0. Why? Because your probability to go to the left and go to the right is the same. So it means that on average, you're going to stay where you are. But x squared average is not 0, and it's behave linearly in time. Or if we take a square root, I will get a quantity which is called the root mean square. That is behaving famously as a square root of t. And we're going to see it in simulations. Okay, so that was the logic of the Einstein and Smoluchowski. They done kind of slightly different things, but everything around this logic. And the Langevin said that he can do it infinitely more simple, according to Langevin. So that I think is a kind of translation from the paper. And he suggests, why cannot we write? Okay, does this equation account for the diffusion in two-dimensional space or three-dimensional space? If it is two-dimensional, how do you use this to understand how to move particles in the 3D? No, I mean, this is one-dimensional case, but you can do absolutely the same game in 2, 3 dimensions. But of course, in that case, here you need to expand using the gradient. Yeah, so you say that you can shift by the small vector r, so you can do it component-wise, and you will get in that case on this side something like a Laplace operator. Yeah, or you can do it component, and you can, I mean, here you can do it in generic ways using some standard tensor analysis tricks. You can do a small vector in the direction r and expand around that vector, and you're going to get absolutely the same equation, but now it's going to be three-dimensional. and kind of like if you need to add forces, you can add forces. And in this case, I mean, diffusion equation is the very simplest case from the kind of stochastic and near-stochastic analysis of something just called Fokker-Planck equation. And in some sort of standard course of non-equilibrium statistical physics, so where kind of you consider not only equilibrium states and quasi-static transitions between them, it's a kind of standard thing. So like if you just open any textbook of non-equilibrium statistical mechanics, you're going to see that this equation is the most primitive, as simple as possible case. But you can go easily to the multiple dimensions, you can include forces, and there is some generic expression. Okay, but I just give it to you for the historical record, because our main purpose of this introduction is to talk about what Langevin suggested. And Langevin suggested something very original. He said, why cannot we describe our particle with the second law of Newton? I mean, it's a particle, and at that moment, quantum mechanics was not yet there as prominent as it could be. So we have a particle, which is some in the viscous media. So there is a drag, and there is some formula for the drag for the particle in the viscous media, so which is coming with the velocity, and this is viscosity of your liquid or of your suspension, and there is a diameter of the particle. So this is a formula for the spherical particle. And probably some of you in the physics undergrad, those who have done the undergrad, have done an experiment of measuring this coefficient. Okay, so, and the motion, according to Langevin, is caused by some fluctuating force. So there is some force which is coming from all possible directions, and it's coming randomly. And that's why it kind of pushes Brownian particles. So as a result, particle is in the media. It could be moved, or kind of it's slowed down by viscosity, but it could be pushed randomly. Okay, so you just get the second law of Newton. That's it. So acceleration, drag, random force. And now you say, okay, so what we want to get something like this. So we want to get the result of Einstein. But here we have equation for x. So what can we do? We first can multiply everything by x. We get equation like this. And now we need just to bring it to the equation for the x squared. So, and there is a couple of mathematical tricks. This is very easy. Yes, x dx by dt is just 1/2 of d by dt of x squared. But if we took d2 by dt twice x squared, we're going to get something like this. Yes, so we get two velocities essentially on x d2 by the dx twice. So we get this term. So what we have as a result that this term is equal to half of the second derivative of the x squared minus essentially velocity of this particle. So we can put it back to the equation. Our force is now multiplied by position. And now what can we do? We can just average out over everything. And kind of over the possible kind of direction of the forces over the all possible particles, and we add in this symbol. And what will happen? So of course, we just add this symbol, but now we need to see what we have. These guys we keep as they are. So for this guy, what is the average of the v squared? We need to use Lyrial theorem from the classical mechanics, which is saying that on every degree of freedom in the system, you have half of the kT. Yes, so kind of we have here only kinetic energy, so half of, so average over the kinetic energy is 1/2 of K Boltzmann T. Yes, so and what's happening to this term, because of the fluctuating nature in different directions, average of it is going to be 0. So essentially, we don't have anything related to this fluctuating force in this particular equation, but that will be enough. So we get the equation like this to derive the equation for the x squared. So we can integrate once this equation. We're going to get some constant, which is coming with temperature, and exponential constant. And according to Langevin, he estimated this term, and kind of exponential is dying out on the time 10 to the minus 8 of second, while this motion of the Brownian particle was macroscopic motion, which people were watching in the microscopes, like with the kind of on the real time scale, not on the 10 to the minus 8 seconds. So it's happening on the, I don't know, milliseconds, which is a 5 orders of magnitude difference. So he just dropped this term, and what he get that the x squared is essentially behaving exactly like in an Einstein derivation. Okay, so this is a little historical excurse into the how the stochastic terms come into the description of the physical systems. Okay, and the equations like this, because in fact you might ask, oh, we don't even use this f. Why we need it here? In fact, we need it here if we want to calculate some different quantities. And I'm going to show you now on some other example which quantities are we talking about. So Langevin equation is one of the examples of what is called stochastic differential equation. And this is just a differential equation which has a stochastic part in it, or random process in it. And there is a correspondence between the stochastic differential equations and the equations like diffusion equation, which is in general case for this kind of for the classical stochastic differential equation will be called Fokker-Planck equations. Okay, so Fokker-Planck equation in kind of quite general case. Okay, I mean this term might be some generic diffusion metrics as we're going to see, but you can do the stochastic differential equation if you can factorize it like this. So it's equation which is looking like this. So it have some term here, so kind of the first derivative, and this could be function of x and t, and the second derivative of our p, and p is the probability distribution of quantities. So here we're talking about p is a probability distribution which is describing some quantities x1, x2, xn, and t. So it could be like, for example, n Brownian motions. And in this formalism, you can, for example, incorporate interaction between them, or you can incorporate external forces. And there is a statement that this kind of equation is equivalent to the following stochastic differential equation, where we're looking on something like a second law of Newton, yeah, or not really second law of Newton, but for the quantity x. But okay, x dot is equal to this vector A, because this is component-wise sum, yes, and the matrix B on E of t, where this is a fluctuating force. So, and this fluctuating force is already not just something fluctuating, it's a well-defined force, which is average over two different times is, I mean, it's a delta correlated and orthogonal, so only if E is equal to G, it's not zero, okay? So, and now why these terms and these terms have a certain name. So this is called a drift vector, and this is called a diffusion matrix. And why is a very simple answer, that if we calculate the equation for x dot, we're going to get expectation value of A. So what does it mean? It means that it's described to you kind of, because this is the velocity of your x, and that is proportional to this term. So it means that it's a drift term, yeah? So, and if we calculate the xk xl expectation value, which is related to the covariance, or if it's the same, that would be something like xk squared expectation value, we're going to get a couple of terms like this, but mainly it will be proportional to the symmetric combination of these guys. And in this case, that will be this will have the symmetric properties, but in general cases could be some arbitrary diffusion metrics. Okay, so these structures are called Fokker-Planck equations, and what we want to relate these structures to some physical systems which are relevant for quantum systems. And there will be one example of this Fokker-Planck equation, which I suggest that you try to implement, and you'll see how. So if we have one-dimensional particle, which is kind of damped and diffused, and it's described by equation like this. So you have some constant k here, x, diffusion constant, second derivative of our probability distribution. It's equivalent to the equation which is looking like this. X dot is equal to minus kx plus square root of d on this fluctuating force, which is delta correlated. And this, by the way, is the space for freedom. So you could, because what is a delta correlation? It means that only if these two forces are acting at the same moment of time, they give you a result. Otherwise, they're not giving you a result. But you can create a little bit of memory. So you can have here, for example, exponential correlations and some other structures which people do. And using that, they come to the different types of noises, because this is acting as a noise. So we can formally integrate this equation. And we can, of course, get equation for the average. So kind of this fluctuating part doesn't matter. But if we now calculate the variance, yes, and the variance is expectation value of your current solution minus average solution, and this is our average solution squared. So if we just go through the math carefully step by step, we're going to end up in expression which is looking like this. And for the long times, this term goes away, and we have only constant which is equal to the diffusion constant on the two drag constants. Okay, so and that is already place where you can see that this d is playing a role. And another place where the D's playing a role is when you try to calculate things like two-point correlation functions, which are telling you how the kind of motion of the particle related to each other between the different kind of time moments. So, oops, where is my beginning of the two-point correlation function? So if we calculate average over xt xs minus just average over the xt and xs, just to remove the first so-called first moments, what we're going to get if we go through the kind of, again, carefully through the math, the only tricky moment here is when you calculate this integral, what you need to see, because when you calculate the average over the E and the S, you're going to get a delta function. And in that case, you're going to have a situation where the delta function might not have a might not have an x of implementation, because you have something like t prime minus s prime. And in this case, you need to see that this quantity is still belonging to your domain, and that's why here you get some absolute value. So you need to consider the case when the t prime is greater than s prime, and s prime is greater than t prime, and afterwards put it together. Okay, so but if you do it carefully, you get an expression like this. And for the long time limit, so again, this term goes away. But if these guys are both large, we don't know what is the difference, so that we need to keep this term. This correlation function is equal to this expression. And again, as you see, this diffusion coefficient is staying here. And of course, we get a explicit correspondence between our variance, which is just x squared, yeah, and xt and xs. When the t is equal to s, we just get the same expression. And this also very famous and very widely used process, which is called Oersted-Uhlenbeck process. So as you see, it's just slightly different from the diffusion. So it's if you don't have this term, so if you don't have like this damping term or drag term, you will get just a diffusion. Okay. Okay, so how you can measure if our approximation is acceptable and does not affect significantly the result or not? It's a very good question, and there is very simple answer. So if we go back to the Brownian motion, very quickly to the picture, it first started with observations, yes, and there is a history of observations. And afterwards, we're making a whole bunch of approximations, and we see that although we've done this so many approximations, and we get very simple theory, is describe what the people observed, and the people observed that the x squared is going linearly. So kind of your average variance of these Brownian motions. You can have a model for the diffusion coefficient, again, Langevin equation. Where is these guys we know, and from the Langevin equation, we know explicitly, where are you? We know explicitly, sorry. We know explicitly the diffusion coefficient because because there is a little lag in my internet, sorry for that. Yes, so, and everything here is measurable, yes, because temperature is measurable, viscosity coefficient is measurable. As I mentioned to you, you do it in undergrad, you take a small balls and throw them in the oil, and you time how slowly things are falling down, and you measure the viscosity coefficient, diameter is measurable. So you can have an estimate of the diffusion coefficient. So you can estimate how quickly this x squared is propagating, and you can compare with the experiment. And that's a trick. You just compare, you do the theory, you do the approximations, they sound logical, at least they sound, for the person who's inventing them, they always sound logical. But if they also have a good agreement with the experiment, you won. You have a little model which describes to you evolution. Okay. So now, very, very quickly, I will introduce to you, because we're mainly talking about final dimensional systems, and in the examples, we're always talking about spins. So, but because Brownian motion is kind of particle which is wobble around, moves in the medium, kind of its unraveling is much more close, or its quantum version is much more close to the oscillators than to the two-level systems. So let me just say 2 words about open quantum system for the quantum harmonic oscillator. So of course, quantum harmonic oscillator, as we all know from quantum mechanics, is described by the Hamiltonian like this. Yes, so just where I just throw away the vacuum energy term because we don't want to deal with what to do with vacuum energy, so we can always shift it. So, and the A and the dagger creation annihilation operators, which are of course acting in the following way on the basis vectors. And the density matrix in that case of the quantum harmonic oscillator could be written like this, as just an infinite matrix, NM, kind of it's a kind of discrete but infinite representation, where this N and M, they of course form so-called Fock bases in the Hilbert space of the harmonic oscillator. It's called the Fock state. It's not a usual Hilbert space, yes, because you need to remember that the harmonic kind of, this is bosonic commutation relationship. So it means that you take a normal Hilbert space and symmetrize it. And the kind of the bosonic version, and if you're dealing with fermions, you anti-symmetrize it. So that's why this space is called Fock space. And of course, this is kind of subspace of your Hilbert space where all the symmetric wave function lives. And of course, these states are normalized. Okay, but the reason why I'm telling you this story is because there exists a whole family of the linear combinations we can build, including infinite ones, such that these vectors are kind of eigenvectors of the annihilation operators. And this is a very special state. They're called coherent states. And if you go to any book on quantum optics, or if you just apply to this equation, these rules, you can derive that in the Fock basis, coherent state is defined like this, where alpha is a complex number. Okay, so alpha forms the basis, but it's a very interesting basis in the difference to the Fock state because it's overcomplete. What do I mean by that? That when you have alpha alpha, it's equal to 1, but alpha and beta, so two coherent states, they're not orthogonal to each other. And alpha beta modulus squared, because there is also kind of complex conjugated part, but alpha modulus squared is given something like this. So as you take two coherent states which are far apart from each other, they become to each other orthogonal. But as they get in close in the space of all possible coherent states, they are not that orthogonal to each other. Okay, and if they form bases, we can have a resolution of identity. And now there is an interesting bit, like how to put it, the general form of the density matrix for the Fock states will always have non-diagonal elements. Some specific states, like a thermostate or some other state, they might be diagonal, but the generic state is non-diagonal. And there was a very nice idea, which was suggested by the Glauber and Sudarshan. And they say, okay, take into account that these states are overcomplete. The information which you have in the diagonal by these states might be enough to describe everything. And they create this object, or it's called quasi-distribution. It's analog to probability distribution, which is called P single or P representation. And it's defined like this. And there are some rules how to work with these objects. What is interesting for us, this is something like a probability distribution. And for this object, we're going to consider some examples of the Fokker-Planck equations. Or you can have another object which is called Q function, which is vice versa. Again, it's also you're saying that you're going to take the central part of your density matrix, but you take it like this. And Q and P functions are related to each other. But they're also related to some other structures which are related to the path integrals which are constructed in the space of these states. But that's again, if you are interested, you can always go to this kind of about that, probably some advanced book on quantum optics. But now that's what I want to introduce to you. There are many other representations which you can do. There is a Wigner phase space representation, which is very famous. There is also so-called R representations, and you can introduce as many as you like. But for our purposes, it will be enough P and Q, even P will be enough. Just for the completeness, I wrote Q. So if we now have a quantum harmonic oscillator, absolutely in the same spirit as we had the two-level system, we could consider quantum harmonic oscillator in the heat bath. So, and if we go all the way, we're going to get equation which is looking like this. And the meaning of everything is identical. So because this is annihilation operator and creation operator, so this process describes to you the process when your harmonic oscillator is losing photon into the bath. This term is describing to you the process when the harmonic oscillator is gaining photons from the bath. And exactly in the same way as you have sigma minus, sigma plus, and sigma plus, sigma minus for the two-level systems. Yes, so one was describing when you emit, and statistically you emit more often than you absorb. Okay, so in Hamiltonian, the quantum harmonic oscillator is just a standard Hamiltonian which is written to you. Gamma is the spontaneous emission coefficient. Again, absolutely the same meaning. Spontaneous emission. So why spontaneous emission? Because at zero temperature, we don't have this term, and we have only this term, but without average n. N is a mean number of photons on the frequency of transition is equal to 0. So, but we're going to still have emission down, even if the temperature is 0. So if our bath is empty at zero temperature, 0 Kelvin, we're going to still have emission. Okay, and the n is, yes, Bose-Einstein distribution, which the physical meaning of this constant is just average number of thermal photons in the bath, which can interact with your system. So kind of in the both cases, it's absolutely the same, in the same formula for the two-level systems or for the harmonic oscillators. The only thing which you need to keep in mind here is the frequency of harmonic oscillator, and in case of the two-level system, here you would have a frequency for the two-level system. And now we can use this ansatz for the P function to substitute it into this equation. And this is a little bit of work, and you can just take my word for it. And what you will get, you're going to get equation which is looking like this. And kind of, again, in the books, like which are recommended, for example, in Carmichael's books or in Wolf Milburn, they definitely do the derivations of this equation, and they even solve this equation. You can solve this equation because it's a kind of solvable equations of the second order from mathematical physics, and there are multiple ways to solve it. But why we want this here? Because we can see this as a Fokker-Planck equation and treat it as that we have the P is the function of alpha and alpha complex conjugate. This will be our drift terms, and this will be our diffusion term. And we can rewrite, instead of solving this equation, we can rewrite it for our kind of axis. And one is the alpha and another is alpha complex conjugate. So this is our drift term because it's going with alpha and alpha complex conjugate. They're getting here. And here we would have something which is looking like B dagger B transposed. Yes. So if we just give a look on this D, so if we take this matrix, we can rewrite it like this. If for the B, we choose matrix which is looking like that. And in this case, we need now to add our fluctuating forces. So instead of solving this equation, we can just solve this system of equations, or these two equations for alpha and alpha complex conjugate. And the price for that, kind of the fact that we can deal now with alphas instead of so because, okay, so this is equation of the second order. And we reduce the kind of, in some sense, the level of the equation, but the price for that to the first order equation, but the price for that is stochastic forces, which again are delta correlated. Okay, so we can now rewrite it back in the form of alpha and alpha complex conjugate, and now we can solve it. Yes, so, and we can also rearrange eta 1 and eta 2 in this form, and we can check that this will be this equation and identically the same equation but complex conjugated. So we can essentially solve one equation where this eta new kind of stochastic force, which have a real and complex part, is delta correlated as well. This could be checked directly by just substituting this form. Okay. Okay, so now in solution of this equation, because the equation is identical to which we've seen in the Orsten-Uhlenbeck case. Yes, so we have just a constant here on fluctuating force, so we can use the ideas from there. So an average alpha will be looking like this, exactly as x, and the quantity of interest here. And what is alpha? Alpha corresponds to average over the annihilation operator, and alpha complex conjugate will be kind of statistical average over the creation operator. And this could be related, for example, to the average of your electromagnetic field, which is created by which is related to this quantum harmonic oscillator, or it could be related to the average displacement, because x, yes, x for the harmonic oscillator is proportional to a plus a dagger. So you can ask the question, what is average x? And that will be proportional to average a plus average a dagger, yes? And this a and a dagger are exactly these alphas. But we can also calculate something more interesting. We can calculate what is the expectation value of alpha complex conjugate alpha. And we're going to get formula which is looking like this. And this quantity is of interest because it's expectation value of a dagger a, which is number of photon operators. So we can see how the average number of photons behave in this case. Okay, and as the time going to infinity, obviously from this expression, these kind of first order moments are going to 0, and the second order moment is approaching the constant, which is the number of photons in the bath, which is again absolutely physical and expected, because that's what this equation describing to us. Okay, even this equation. This equation is describing to us how harmonic oscillator exchange heat with the thermal environment. And when it thermalizes, we expect that the properties of this quantum harmonic oscillator will be exactly as the properties of the temperature of the harmonic oscillator will be exactly as the temperature of the heat bath. And what we see in this case, that the average number of photons when the T is equal to infinity, exactly equal to the average number of photons at this temperature in the bath. Okay. These equations are exactly the same if we would solve equation Fokker-Planck equation. So if we would solve this equation, find the P symbol, and afterwards just proceed in a standard way to calculate, for example, so if we would need, for example, what is the A dagger A, we would need to calculate something like trace of A dagger A rho, and afterwards we would use equation for rho. So I can just write it like this. So we just have some integral into alpha over pi, and we would have alpha alpha projectors. So we're going to have alpha modulus squared p of alpha alpha complex conjugate t. So we'd need to calculate integral like this, and in that case we are going to get exactly the same expressions. And again, if you are curious how to derive it and how to play this game of jumping between the stochastic differential equations and the Fokker-Planck equations, you can do it, and you can read about it, for example, in Carmichael's books, in the Carmichael book, or in the other books which are recommended in stochastic processes, and this could be done. Okay, so this is one of the ways how we can use stochastic processes to solve or to describe open quantum systems. Yes, so kind of if you're going to have a kind of more complex system, not just a single harmonic oscillator, but for example, you can have a harmonic oscillator which interact with the two-level system, and they're both coupled to the bath. You're going just to have here more equations, more forces which you need to take care of. Okay, so but now let's go from slightly different approach, and in order to do it, because kind of this is one approach which is based on the Fokker-Planck equations, but the Fokker-Planck equations not always existed. And the question is, can we also do something related to the stochastic? Can we go from the density matrix equation to some stochastic equation for the wave function, which is called stochastic Schrodinger equation, in the general case? And answer is, I mean, if we are dealing with the master equation in GKLS form, the answer is always yes. Okay, so very naive approach first. So we're considering 0 temperature bath. So mean number of photons is equal to 0. So, and also we're going to throw away for a second Hamiltonian so that it don't bother us. We're going to get this simple equation, and let's look how this equation looks after the small kind of final difference, t plus dt. We can write it these terms plus these terms. Yeah. So why there is a reason to rewrite the stuff like this. So we have everything here. So what will happen to harmonic oscillator when we are multiplying it by a dagger f from left and from the right? Nothing, because this is the number of particle separators. It doesn't change the state of the density matrix. I mean, it doesn't change the number of photons. While this term is changing the number of photons. This term is describing to us the jump process. Essentially, this part And we can see it like this. So kind of what could happen with your density matrix at the next step if it's described by this equation? It could remain as it is, or it could jump. So it could lose photons. So, and it's very nicely seen that if we assume that we are in a pure state, so we're with a state with a given number of photons, and in this case, so at rho t is just a given number of photons, in the next moment, we're going to have something like this and something like this. Yeah, so kind of we're getting statistical mixture of remaining in the state n and doing the jump. And you can see these terms as the probabilities, yeah, because like as a way of writing of the density matrix, we could see that this is a probability that we remain in this state, and this is the probability that we are doing the jump. Yeah, so we have two events, yes, one photon loss, so that this pure state and n is jumping into this state with this probability, or we have no loss with this probability. Okay, so, and now we're getting closer to the idea of unraveling. So if there is no photon loss at this moment of time, what is the conditional state? So what will be kind of like, if you're saying like, let's assume that we are in this branch, yeah? So if there is no photon loss, what is the state of the density matrix? So in kind of generic case, not for the n photons, it could be written like this state, yes, evolution according to that state, and we need to normalize it. We need to divide by trace of it, and just using the fact that trace is linear operation, so this is, we can expand it and write this in the powers of delta t, and we're going to get expression like this. So where this is our conditional density matrix, and with the dt, we have this very interesting expression, which also should immediately indicate to you that when you're going to talk about this unraveling, you suddenly become inherently nonlinear. Yes, because what's that? My conditional density matrix is now not just some linear expression of my density matrix, but also a function of the density matrix here and the function of the density matrix here. Yeah, because what is the A dagger A conditional? It's a trace over the density matrix. So this is something which you don't see usually, kind of in the standard quantum mechanics or even in the standard open quantum systems. And now kind of we need to make a little jump in thinking, and we can introduce a classical Poisson process. So what is the classical Poisson process? Classical Poisson process is this kind of dn. So it's something which could happen or not happen. So it could have two values, 0 and 1. Yeah. So it could be 0. So this dn of t could be 0, or it could be 1. What did we now? We don't know. But what we know that the expectation, so or mean of this process, is related to number of photons in our cavity. So we just need to take a Poisson distribution, yes, the famous like this, and the mean of this distribution is related to our current state of the number of photons. And what this term is going to describe us, are we going to jump or not? And we can rewrite this equation, and don't be scared because this equation is very easily simulatable, and that's what we're going to do in this kind of a little bit dangerous form, where this term is describing to us jump, because you see it's looking like ax a dagger divided by the trace. So it's kind of, it's doing the jump and normalizing the density matrix. And this term is describing to us evolution when you don't have a jump. Okay, so in this, you can recognize that this term has some resemblance with this one. Okay, so, and what we're getting by kind of, and now what we do. So what do? We're going now to simulate this kind of equation. What does it mean? It means that we're going now to do some evolution according to this equation. And afterwards, we're going to take a random number from our Poisson distribution and decide, are we jumping or not? If we're not jumping, we're evolving again. If we're jumping, and afterwards evolving. So as a result, we're going to get a history, kind of a historical records of our jumps, and our final density matrix is going to be the sum over the all possible histories of our jumps, where this is the probability of the corresponding history, and this is the conditional density matrix. But what is more interesting, that if our density matrix is given by the pure state, we can rewrite it in this form, where this is identically the same equation, but for the wave function. And this is to you a very simple example of the stochastic differential equation for the wave function. And this wave function, the numerical solution of it, kind of on average, will reproduce our density matrix. Okay. So, but now the question is how to simulate these structures. And the simulation process is much easier than it's looking in the formulation process, because the simulation is very simple. So if we have the wave function at some moment t, psi of t, we need first evolve it for the very small moment of time using this non-Hermitian Hamiltonian. Yes, kind of using, sorry, let me kind of, where we were, yes, using kind of this, we need to add this to our Hamiltonian, because we need to separate evolution from jumps. And in this case, of course, the price for this, that is going to be non-Hermitian. Okay, so of course, your wave function is not going to be normalized, or you can formalize, you can see it as the evolution under the non-Hermitian Hamiltonian, which is looking like this. And this state is happening, no jumps, with probability, which is of course given by the length of this vector. And the length of this vector could be approximated by this expression 1 minus p, where the p is the probability, essentially, of the probability of jump for the small time delta t. So in the most of time, you undergo the non-Hermitian evolution, and in some time you jump. Okay, so now we need to decide when it's happening. So what do? We just take a random number from 0 to 1, and if that p, the probability of jump, is smaller than r, we jump. Yes, so we take this non-Hermitian evolution and apply our jump. Sorry, if p is smaller than r, there is no jump. So we just normalize our wave function, because we would like to deal with a normalized wave function. And if p is greater than r, we're doing the jump, but afterwards we also normalize. So that at every small step delta t, we're dealing with normalized object. And we repeat it until, with our iterations, we're going to reach our final state. This procedure could be clearly and straightforwardly generalized for the generic case. So if we get master equation like this, for in GKSL form, it could be rewritten like this, where this non-Hermitian Hamiltonian is looking like this. Yeah, so the same thing, we just put in all these terms back into the Hamiltonian, because they don't describe as jumps. Our goal is to separate non-jump part and jump part. Okay, so this is happening without jumps, and this is describing to us jumps. And now if we just write density matrix by definition, yeah, as a sum of wave functions, we get getting that the derivative of our density matrix have the following form. And this part is looking like just a standard Schrödinger equation or Liouville equation, which is evolving under this non-Hermitian evolution. And what this part is describing us is describing quantum jumps from the state psi j to some phi jk, where it's a jump over with jump operator ak. Okay, again, we need to calculate what is the probability of jump and no jump. So the total probabilities of all possible jumps is the sum of all possible jumps. So we can calculate that we get a probability of jump. And now we get an algorithm. We start with the some psi j at moment t. We non-Hermitially evolve it, pick a random number, and decide, are we jumping or not jumping? Afterwards, we need to decide again how many, what kind of jump are we doing? Because in this case, we get n squared minus 1 possible jumps, yeah, or whatever. So if this delta pj is smaller than r, there is no jump, and we just normalized our non-Hermitian wave function so that it's remain normalized by 1. If delta pj is greater than r, we need to jump. Now we need to decide which jump are we doing out of these k possible jumps. So how do we do it? We just we draw another random number, and we treat that we jump with the k jump with the probability pjk over the pj. So because pj is the sum of all of them, so distributions like this will form a probability. So we just draw a random number and see in which area we end up. And if we end up in the case area, it means that we're doing jump number k. And of course, yes, we do the jump and we normalize so that our density matrix is normalized. So we repeat it until we finish our steps. And afterwards, when we get all the record of the evolutions, we can, of different psi j's, we can average to get our density matrix. And by the way, yes, if we have multiple psi j's, like as it's written here, so we need to do this procedure many times, and we're going to see it in the tutorial. So when we're going to have it, I'm going to give you the examples of the trajectories and examples of the averaging over them. But also, if your initial density matrix is not a pure state and you're starting from some mixed state, you need to do this procedure for every wave vector which is a part of it, and afterwards average also over that one, so kind of to perform this sum. Okay, so that was kind of a naive approach, or it's something like what is called in the normal differential equation will be called Euler scheme, or kind of it's also called Euler scheme for the stochastic differential equations. But now what we're going to talk about, how we can do it with the finite differences. So, and I'm also going just to give you a general theory, and this theory is wonderfully explained in Francesco's book. And if you are interested to know where the formulas which I'm going to talk about are coming from, you're welcome to go to the Francesco's book, which is somewhere here. Yes, the theory of open quantum systems. And you can read the corresponding chapters, but I'm going just to give you a very brief overview how it works. And it's called stochastic unraveling with the piecewise deterministic process, because it means that we're going to have a pieces of the deterministic evolution, non-Hermitian evolution, but not for the infinitesimal times, but for the final times. And afterwards, we're going to have an option again, jump or no jump. No, we're not going to have an option. We're going to jump. So we're going to detect the piece of evolution. So we're going to, the idea will be to determine the piece for which we need to evolve with using non-Hermitian Hamilton, and afterwards we jump. Afterwards we evolve again and we jump. And the trick in this approach is, yes, Francesco, answer for your question is yes, because I almost finished the lecture. The difficult part is to determine how long are we going to do this non-Hermitian evolution. Okay, but I'm also going to comment on that. So we're starting again with the GKSL equation. And the corresponding stochastic differential equation is looking like this. And you see, you have all the tricks, or kind of all the terms as we have before. Yes, we have some non-Hermitian part, which will be a little bit more than non-Hermitian part, but for practical purposes, it's non-Hermitian part. It's also have nonlinear terms, but it's for the theory. It's not for the actual simulation. And the jump parts, again are happening according to the Poisson distribution. And the Poisson distribution, kind of the Poisson stochastic increment or Poisson process, is just 0 or 1. 0 means no jump. 1 it means that you're jumping. K, the jump operator, and I think I was thinking that the square root of gamma k is forgotten here, but if it's not here, it's also not here, so it could be cancelled out. Okay, so Poisson increments are correlated, yes. So n squared is equal to n, and expectation value is equal to exactly as we had before, something like kind of psi a dagger a. So kind of it's a probability of the corresponding jump channel. Okay, and this g of psi is non-Hermitian part, which we already seen, and plus some nonlinear part, which is unnecessary for the simulation purposes and only important for the generic theoretical consideration. Okay, so and now I'm going to talk how you can simulate this equation. So it's not simulated for small deltas, it's simulated for the finite times. But these times you need to take from what is called waiting time distribution. And that is kind of the problem of this method, that you need to solve equation for this guy, and in general case you can only solve it numerically, and this also could be expensive. So for your real method, you need to see, can you do a lot of small steps, or can you, if you can have a nice procedure of inverting waiting time distribution, you can probably go for this approach. So how the algorithm is looking like. At the time t, we have some psi of t. So we need to first find out for how long our psi of t is going to evolve non-Hermitially. And that we need to find from the waiting time distribution and how it's done. So we have our non-Hermitian part, kind of evolution, multiplied by our state. So we need to calculate this absolute modulus squared. So we just evolve the state and calculate its length. So now we equate it to the random number from 0 to 1. So we draw a random number. We write, for example, 0, 1 is equal to this. And the task will be for your current psi to find the tau, for which tau this thing is equal to 0, 1, which we just draw. And again, in general case, you can only do it numerically. Essentially, you just plot a graph of this. You can say it, eta of tau, and oops, it wouldn't have it, so it might have behavior like this, and 0, 1, it won't be larger than 1. So, but I mean, this graph, the shape is dependent on your psi of t, is strongly dependent. And essentially, you plot the graph, and afterwards, by choosing eta, you need to solve kind of inverse problem. Okay. So, but this is the only difficult part in this method compared to the interphysimal one. Okay. So, and in order to continue, what we need to do, we need to find so-called the defect q, which is when this tau is equal to infinity. And if eta is greater than q, so because what will be q is like where it will converge. Here I draw you that it's converged to 1, but sometimes you could have it that it's converged to something which is smaller than 1, something here. And in this case, yes, if eta is greater than q, then we can find tau its existence finite. And if eta is smaller or equal than q, then it means that the tau is equal to infinity and there will be no more jumps. And you can just do the evolution. Yes, so, and if we know tau, now we're set. Because if we know tau, we can evolve our state non-Hermitially, afterwards we jump. So yes, so if we know tau from waiting time distribution, we can evolve our state divided by the norm. So our state from the times from 0 to tau in this interval for the all s's, which are from 0 to tau, is described by the wave function like this. After time t plus tau, so in the end of this, we are always jumping. We're not already deciding are we jumping or not. We are always jumping. Of course, yes, we're jumping if tau is smaller than infinity, or t plus tau is not exceeding the limit of what we want to simulate. And if there are many jumps, we just choose out of the jumps, again, which one will happen. So we jump with corresponding probability pi. We do the jump, and we iterate these steps. We iterate these steps, and what we'll produce some wave function, which is going to look like, I don't know, some process, and so on and so forth. So and afterwards, you do it many, many times. In a good case scenario, so you want to do it 10 or maybe even 100,000 times, and you average. And what you are getting in return, in that case, what you're going to get the density matrix as the average over the all possible realizations or all possible wave functions. So yes, generate many realizations of psi of t and average over them. Okay, so this is essentially the theoretical part of today's lecture. So now we're going to do a couple of numerical experiments. If there are any questions about the theoretical part, I'm happy to address them. Otherwise, we'll go to the tutorial for notebook. Okay. I need to reshare my, sorry. Okay, I assume that now you can see my screen. So, and what we're going to do first, we're going to do a couple of plays with the Brownian motion. Yeah, so, oops. So, and the Brownian motion will be very simple. So we're going to do 1 and 2 decays. So in just next coordinate of your Brownian particle is just previous coordinate plus random number from -1 to 1. And we're going to calculate how the x squared or r squared for the 2 decays behave, and it should be behaving like n. So we should have a linear dependence on time, or for the square root, and this quantity is called root mean square. It should be behaving as a square root. Okay, so we're going to do 10,000 steps, and we're going to do 500 trajectories. So we're going to generate 500 different Brownian motions, and when we average over them, we're going to get our example. So let's go something very simple. So let's generate Brownian motion. So we get 500 trajectories and 10,000 steps. And what we do, we just, for each trajectory, we calculate, we record our kind of position, and afterwards we add in extra random number from -1 to 1, because random is just numpy random is giving us random number from 0 to 1. Okay, so now after we've done it, we can of course plot it, and you see I get some kind of graph which is different from the previous graph because we have randomizations. If I'm going to do it again, it will definitely change. Yeah. So our Brownian particle is starting here, then time is progressive. For example, the blue one is wandering like this, the orange one is wandering like that, the red one like this, and so on and so forth. Okay, so now we can do a little bit of, besides nice picture, we can do a little bit of kind of calculation. So we can calculate what is mean, and mean in this case will be just we sum, I put axis to 0, and the first axis is trajectories, because we need to average over the all trajectories. We need to take position of the Brownian walker after the first step on the all trajectories and average over it, position of the Brownian walker after the second step and average, and so on and so forth. Yeah. And the same thing for the variance. So because we need to average over the x squared, and the x squared, when you write in Python matrix multiplied by matrix, but not dot, but star, it just multiply them element wise. So that's exactly what we want. And now we can plot, but this wouldn't change really. We can plot the mean. So this is our mean, which is supposed to be 0. And this is variance, which is obviously a linear relations from the number of steps. Yeah. So if we just increase, so if you're not convinced that this is look linear enough, you can just crank this number to the kind of more number of trajectories, and you should obtain the more trajectories you have, because 500 trajectories is not too much. You should obtain the kind of more and more straight line. Okay, so let's go into the 2D. 2D is almost the same. Sorry. Okay, so but now what we have 2 arrays, one for x's and one for y's, and we could skip the generation of the array for x's because we already have it. But otherwise, it's absolutely the same thing. So here we store x's, x coordinates, here's the y coordinates, and we have the increments with the random noise. Oops. Sorry. Oops. Okay, and now we just plot, because now we have 2 coordinates, x and y. There is no way to put kind of time on the axis. We're just going to plot them continuously, and you see kind of we get slightly different pictures. So we get So 0, 0 is where they start, and the green one went in this direction, the red one goes like this, orange one like this, and the blue one and violet like that. And of course, this is just the index of the trajectory. You're welcome to change it, to play with the code, yes, and you can plot more, and so on and so forth. Okay, so now we can do some analysis again. So and now we're going to plot three quantities: two-dimensional mean, root mean squared, and the variance. So two-dimensional mean, in order to calculate the two-dimensional mean, which we again also expect to be 0 as a function of time, what we need to calculate? We need to calculate means of the x coordinates, means of y coordinates, and afterwards take a square root of mean values of x's and y's in each moment of time. Yeah. So root mean square is kind of vice versa. So you just swap the order of taking sum and the multiplication, so or averaging. So we're square root of a squared on a squared, b squared on b squared, and afterwards we're taking the sum. Yes, and divided by the number of trajectories, and variance is the same thing but without square root. Okay, so now we can plot. Okay, so mean is 0, root mean square we're going to see now. First of all, variance is clearly linear, but now let's see the root mean square, and for that we need to close the variance. Let's just and obviously root mean square, if the variance is linear, root mean square is, of course, should look like a square root, which we can see perfectly fine. Okay, so and the last example which I'm going to talk to you about is this naive idea of unraveling of the quantum harmonic oscillator at 0 temperature. Do you have any questions by the Brownian motion? And if you think that you understood how I've done it all, you can just play around and do it, for example, for the Ørsted-Uhlenbeck process, which we had in the lecture. And again, we have an analytical calculation, so we know what to expect from the, for example, x squared of the Ørsted-Uhlenbeck, or you can also numerically calculate the two-point correlation function. And again, because of the analytical calculations, you know what to expect, and you can see how quickly things are converging. But now let's go to the unraveling. So again, for simplicity, let's drop the Hamiltonian part, and we're going to start with the pure state of the n photons. And quantum master equation, which we're going to unravel, is looking like this. Yes, so it's at 0 temperature. So observable, which we are going to look at and which have a meaning for us, is number of photons. And analytical solution for that, which we're going to compare to, is looking like this. So average number of photons is initial number of photons multiplied by just exponential. So essentially what we're going to do, we're now going to do a glorified simulation of exponential decay. Okay, so and what will be our algorithm? So we're going to keep the record of the trajectories, but now the question is how you're going to keep the record of the trajectories. Because formally, if we are starting, I don't know, from some n photons, we're going to have a vector which is going to have n+1 components, at least n+1 components. If we could have excitation, it could be even bigger. And in general case, the vector in the Hilbert space for the Fock space, sorry, is infinite. But because we're in a such simple scenario, we know that only two things could happen to us. We could have a given number of photons and remain having the same number of photons, because there will be some non-Hermitian operator, but due to the fact that if we start with the n photons, non-Hermitian operator is going to do a phase factor, and that phase factor is going to cancel out with normalization. So we can have n photons, or if we jump into n-1 photons. And that's the only thing which could happen to us. So from this point of view, it could be very easily written like this. So we're going to keep record of the number of photons, and for that we need only one number. How many photons do we have now? So we're generating random number r from 0 to 1. And for some small time t, if p is smaller than r, nothing is changing. So we're keeping the same number of photons. And if p is greater than r, we're doing jump. And we can do jump only down. So we're going to k-1. Okay, so let's do it. So this is my small step, gamma delta, which is 0,01, total time 5, number of steps which I'm going to calculate. We can just take final time divided by the step size and take an integer. Yes, and number of trajectories for simplicity, let's take 100, and I'm going to take initially 5 photons. Okay, so now the main code, which as you see also looks relatively straightforward. So here we're going to record the trajectories. So, and the trajectories are going to be recorded in the metrics of the number of trajectories and number of steps. So because we want the time evolution, not the final state, but the time evolution. Okay, and we can use the type of data which is float because we know that we only need to record the number of photons, and in principle it could be changed to integer. We initializing everything at the step 0 to the initial number of photons, and afterwards going through the all trajectories, all steps, we generating random number. Sorry, can you please, do you want to ask a question or you? Thank you. There is an echo. Okay, so we generate random number, and afterwards we calculate what is the probability of jump. Yeah, and the probability of jump, we take a previous trajectory on given step multiplied on our gamma delta factor, so our small time step multiplied by the gamma. And now we see, so if p is greater than r, we're jumping. Yes, so because we're kind of keeping our trajectories the number of photons, jump means that we just take this number and do -1. And if p is smaller than r, we're keeping the same number of photons. And now let's just give a look on some random trajectory. In this case, it's 10, and you see it changes. What does it mean? So how the evolution is looking like? So we have 5, 5, 5, 5, 5 photons, and afterwards we get a jump, 4, 4 photons, and afterwards 3 photons, 2, 1 for a very long time, and afterwards, boom, vacuum. So this is a typical example to you of this sort of quantum trajectory. Okay, so now we can plot. So what we can plot, we're interested in plotting few things. Yeah, first of all, we can plot some examples of the trajectories. We can roughly assume how they look like because we can change here how many trajectories I have. 100, so we can do 20. Yeah, so it will be some different distribution. You see this one is quicker getting to 0, and when it's 0, the probability p will be 0. So that is fine. Yes, and kind of we want few examples of the trajectory, and afterwards we want to see what will be the average of all these trajectories, and we also want an exact solution. So let's plot it. Okay, so first of all, this is how the quantum trajectories are looking like. So kind of red, green, orange. So this is trajectories. The average of the 100 trajectories which we've got is the purple one. Yes, you see it's kind of, but if we just crank it to 1,000 trajectories for this process, that would be more than enough so that we could not distinguish between the purple one and the blue one, which is the exact solution. So clearly this is a tool which is working, and you are welcome to use it. And there is one more thing which I need to tell you about these quantum trajectories, because, you know, they're looking very, I would say, and these general ideas of unraveling could be seen twofold, and especially this unraveling in this piecewise deterministic form. You can see it as mathematical trick to solve master equations. Yeah, but people were thinking that what if, when we're talking about individual events, that's really what's happening. Like if you have a particle, I don't know, electron or a bunch of bosons as a quantum harmonic oscillator, and they interact with a thermal bar. Can you play the game, and can you kind of really have this interpretation that this kind of jumps? So this is real evolution of the real wave function, which at random moments of time doing the jumps. And the answer is yes, you can. And when you're dealing with the GKSL equations, the stochastic Schrodinger equation which you get is really describing to you a physical evolution. And there was an experiments where the people were doing some very interesting sets of measurements, which is called quantum non-demolition measurements, when you can measure and you can see what's happening to the quantum trajectories. And so this is not just artificial kind of, you know, mathematical trick. under certain conditions, like as I mentioned to you for the quantum master equations in GKSL form, these quantum trajectories are real. And in some sense, they're more real than the master equation, because master equation is average over possible many wave function, while quantum trajectory is really like it's a destiny of the given, I don't know, particle of the quantum harmonic oscillator. It's going to be in one superposition, it's going to evolve, and afterwards it jumps. And afterwards it's evolving and it's jumping and so on and so forth. And of course, it raises a very serious questions, which people also have, that from this point of view, you get a wave function which is discontinuous, yes, when you do the jump. So you have a continuous function and you do the jump. And something is looking very strange. Yes, so kind of like we always like to deal with the continuous functions. But also the question is, where else do you see the behavior like this? Where else you're in quantum mechanics? Because I completely didn't talk about that subject, but where else in quantum mechanics, when you are dealing with the wave functions, which are wonderful and continuous, you can get a sudden discontinuities. So you have a wave function of the two-level system, yeah, on the Bloch sphere, and it's undergoing some evolution, and suddenly it's up or down, or vice versa, or along the x-axis in this direction and in that direction. When it's happening. Yes. Very good, Kaketsa. You're in the measurements. Because, and this is a very interesting connections between the open quantum systems and the measurement theory, because one could say that, because I mean, as you know, problem of the measurement is still one of the most fundamental problems in the kind of in the quantum theory, because it's a very difficult problem, which is related to the very simple fact that we have two ways of doing quantum mechanics in general. In the one way, along the one avenue, we have a wonderful Schrodinger equation and we have one set of rules. And in the moment when we want to know something, suddenly we apply completely different set of rules, which is called Born rule, for example. Yeah. And this is this is still open academic question, but what the theory of open quantum systems allows you to do, it allows you to see the measurements, or kind of to see the environment exactly that what the environment is doing, it's measuring your system. And the fact that we see quantum trajectories is exactly, you know, this is kind of, as we evolve, is nothing happening, system is evolving. In the moment of the jump, that's a result of being measured by this type of environment. So that type of environment just measured this quantum harmonic oscillator. But because the measurement operation is related to the exchange of energy, the field or the quantum harmonic oscillator have lost the photon. Afterwards, at random instance, you have another measurement and so on and so forth. And there is a kind of very interesting and serious, how to say, approach when the people are trying to look on the how to describe quantum measurements exactly from the point of view of equations of open quantum systems or the stochastic Schrodinger equations, which seems to be quite fitted to that, where you naturally have discontinuities. Okay, so I think I'm done. I suggest, okay, the last thing which I want to suggest you to do, you can try to take this equation which you have played around with, and you can try to adopt this code to solve this equation. It's relatively straightforward. You have also one dissipative channel, but what you need to keep in mind that now when you're going to store your trajectories and your wave functions, you cannot store one number, because now you really need to store wave function, which is two numbers. Yes, so kind of from this point of view, here you should have a comma 2, and the data type will be a complex. So kind of that you're going to store two complex numbers. So that's what you need to keep in mind. But otherwise, you can straightforwardly implement the unraveling of this equation and also produce the quantum trajectories which are happening to this system. And I think that would be a very interesting exercise, because due to driving, you will get a situation when kind of for example, if you're going to plot some probability to find the spin up, after its jump, it's going down, but due to the driving, it increase, and afterwards it will be jumping again, and you're going to get some kind of nice pictures. And if you can generalize that, or kind of if you can do it, that will be, I think, quite an interesting exercise for you to try to see and feel, have you understood how to perform the quantum trajectories and unraveling. Thank you.
Yeah, Ilya, thank you very much. That was quite nice. Thank you. I see that you already reacted to some of the comments in the chat. Are there any further questions for Ilya? Please raise your hands or write it in the chat.
Sorry, can I ask my question?
Please go ahead.
Yeah, okay. We usually think about the environment or reservoir as a kind of harmonic environment, which is described with ladder operators. Do we have another approach for the environment? For example, a spin environment, which is described with spin operators or something like that?
Yes, yeah. You can have, I mean, you can have environment composed out of anything, essentially, as long as you have certain statistical properties. And there are spin environments. There are, and Francesco calls out whole series of papers on the behavior of the spins in the spin star system. So when you have a central spin and it's connected to the spins around it and it's interacts. And that, for example, is important for dynamics of NV centers. Also, people consider the environment which is composed of the fermions. For example, that you can try to describe what's happening to your electron in the quantum dot, but it's also sits in the environment of when your electron is tunneling into the quantum dot, it's tunneling from the environment of the electrons. So you can have environment of the fermions, and now you get an extra kind of difficulty because you can have an electron and a quantum dot with spin or without spin. So, and you can have like fermiona spin environment, or you can have a fermions with a spins, but people do it and you can do it and it's it's fine. Yeah. And pure spin environments are also very interesting when they're not symmetric because they lead to the very complex structures which are called spin classes.
Okay, thank you. I just want to mention something. I know your GitHub repository is almost complete about the resource of Open Quantum System. I just write a post in Medium, let me put it in the chat, and try to collect the other video lectures or with the pedagogical approach. And maybe for those of you who are interested, the other students who are interested and can look at this Medium file. Yeah.
Okay, great. Thank you.
Thank you very much.
It's always good to have materials. Yeah.
Thank you very much. And maybe we should reward this effort with a book voucher.
It's kind of you, Doctor.
You're welcome, Francesco.
Sorry?
You are welcome.
Yeah, no, I think it's fair enough. Thank you very much, Omid. I will make a note that we need to double your book voucher. Thank you.
Yeah, it's kind of you. Yeah.
Yeah, no, it's a pleasure. And sorry, since it's 15:28, and I know that all of us have another appointment at 3:30, I would suggest that we thank now Ilya for his 5 lectures and for sharing with us his wisdom about open quantum systems and their numerics and their computational approaches to open quantum systems. And and I guess we will get out of this Zoom and into the next Zoom for the formal closing of the school. Yeah. So Ilya, thank you very much again, and thank you to the participants as well. But we will do some final closing remark in a minute under another Zoom link. Yeah. So I will see you all just now under the next Zoom link. Thank you very much. Thank you. Bye. See you just now.
Okay.